Good afternoon, sir. This is Roja Raman.
Yeah, good evening, Dr. Roja Raman.
Yes, sir.
Can I start?
Yes, sir. You may please start your presentation, sir.
Oh, okay. First of all, good evening to all of you, and thank you very much. I thank organizers for the invitation, and especially Dr. Roja Raman. And congratulations to Satyabama Institute of Science and Technology for organizing this excellent workshop on LIDAR remote sensing of the atmosphere. So today I will be talking on the applications of LIDAR in combination with the other techniques to address the aerosol cloud interactions. So the outline of my talk is what are the processes involved in better understanding the aerosol cloud interactions and the different LIDAR facilities available at IITM for atmospheric sciences, and the recent Ministry of Earth Sciences initiatives for better understanding on aerosol cloud interactions. And I'll give some highlights depending on the time, and I'll summarize. So first of all, the largest of all the uncertainties about global climate forcing is probably the indirect effect of aerosols on clouds and precipitation. So that's what the current focus is: how to reduce the uncertainty in the effect of aerosols on the cloud microphysics and in turn precipitation. So just to give a brief on the different types of aerosol sources. For example, we have marine sources contribute to sea spray and DMS emissions. These are all natural emissions, and over the continent we have biogenic volatile organic compounds that can contribute to the secondary organic aerosols. And in addition to that, there could be other sources like industrial emissions and which lead to anthropogenic emissions of aerosol particles. And when we come to sinks, both dry and wet deposition, where wet deposition includes precipitation scavenging and in-cloud scavenging. And these are the different categories of particulate matter we have to deal in the atmosphere, which ranges from a nanometer size to centimeter size. So for example, the secondary organic aerosols, when they get converted from gas to particle conversion, it starts like a nanometer. And then you have small iconnuclei particles, then the accumulation mode particles. Then we have dust and sea salt and sand, which are giant or coarse mode particles. Then in terms of clouds, we have the sizes could be of tens of micrometer. And when you see the drizzle and rain, so ranges from 100 micrometer to 1 millimeter. And there could be hail, which is in a few centimeters size. So we had to deal the wide range of particulate matter in the atmosphere. And so these particles also, depending on its size, so it has an interaction with electromagnetic radiation at different wavelengths. So if you look at the aerosols, considering their size, so it interacts well in the visible and infrared radiations. That's why the LIDAR technique comes into play. And when you go to the rain, precipitation, or hail, so the LIDAR cannot do much on that, but the microwave radiation can give us information. So coming to the aerosol cloud interactions, I think morning Dr. Ravi Kiran gave a nice overview, so which made my job relatively simple. So the direct effect is due to scattering and absorption. It can reduce the solar radiation reaching at the surface. So in turn, it can aerosols can cool the climate system. Whereas the indirect effect of aerosols is that it can change the cloud microphysical properties. So it can increase the cloud albedo, or it can increase the cloud lifetime. and it can suppress the warm rain initiation processes, because collision coalescence is the process, the major predominant process in the warm rain initiation, which can get suppressed. So I'll come in detail to this. Then when there are absorbing aerosols, it can even inhibit the cloud formation and can burn off the cloud, which is a semi-direct effect. So the first is the cloud albedo effect. So when there is high aerosols over the continent, there could be higher cloud condensation nuclei and higher cloud droplet number concentration. And when there are for a given liquid water content, the more number of cloud droplet number leads to smaller droplet size, which enhances the reflectivity of the cloud. So you can see for the same volume, if instead of one droplet, if there are more droplets, the reflective surface area of the cloud can get increased. So the cloud can reflect more radiation. So this is the Tommy effect or albedo effect. So the ship tracks are one good example. You can see that how the ship tracks can enhance the cloud reflectivity. This is an evidence for the Tommy effect. Then the other thing is that if there is smaller droplets, see, the polluted clouds can have very small droplets. The small droplets can flow through the airflow streamlines. So in turn, it doesn't collide with the other falling drop. So that's how the collision coalescence efficiency get suppressed, and in turn the warm rain initiation gets delayed. So I'll give you some more example in the coming slides. So in order to understand the aerosol cloud interactions, so we need measurements on aerosol concentration and its vertical distribution, size distribution. Then we need to understand cloud condensation nuclei. So what fraction of aerosols can get activated as CCN or ice nuclei, which are a subset of aerosols. We need to have some information on updrafts, because that also play a role on the supersaturation of atmosphere, and the cloud droplet number concentration and its size distribution and cloud liquid water content, which are microphysical parameters of cloud. Whereas the macrophysics of clouds are cloud boundaries, like base height, top height, and the cloud depth. And the integrated liquid water content, it's called liquid water path. So these are some of the macrophysical parameters. So which out of these, so LIDAR can play a role in these parameters. So LIDAR can be used in deriving the vertical distribution of aerosols and aerosol extinction coefficient. I think the previous speakers have already covered a lot of information, basics of all these information, LIDAR equation, retrieval techniques and all. So, and so these are the parameters which LIDAR can contribute. So now coming to the LIDAR's application in our institute. So we have, I think we have started almost 3 decades back, even when I joined in IITM. So there was a bistatic continuous wave argon ion LIDAR. I think it is almost similar to which was established at the same time in Vikram Sarabhai Space Center. Dr. B.V. Krishnamurthy was the instrumental in that establishment. Here in IITM, my supervisor, Dr. Devra, was instrumental in establishing all these LIDARs for atmospheric science studies. So bistatic argon ion LIDAR, then we have ceilometer for cloud boundaries and boundary layer studies. And we also have a dual polarization micropulse LIDAR, Doppler wind LIDAR, and Raman LIDAR. But given the limit of time, I will restrict myself to aerosol cloud interactions and give some examples of the old bistatic LIDAR. So the bistatic LIDAR, so it was set up in the IITM. There was a argon ion laser which emits green wavelength radiation, and we had a telescope which was situated about 60 meter away from the transmitter. You can see here, it's a Newtonian type telescope where it was having a photomultiplier tube in the eyepiece to receive the backscatter radiation. The one advantage I could see with the bistatic LIDAR as compared to the advanced monostatic LIDAR is that in monostatic LIDAR, you can only get the backscatter cross-section, backscattering information here. So you can get the angular scattering. So even at the same height, you can look at, you can tilt the beam and receiver to different angles to get the information at the same height, which was used to derive the aerosol size distribution and refractive indices. So this was the advantage as compared to the other monostatic LIDARs. So this was so we had, I think, long climatology of aerosol profiles, mainly in the boundary layer. And there were a lot of studies comparing the aerosol climatology and compared with other remote sensing techniques like SODAR for boundary layer studies and all. So, and the other LIDAR is like the ceilometer, which is laser beam laser. Can get up to the backscatter up to 15 kilometer. The advantage with this is because it is in the near infrared, the Rayleigh scattering and molecular absorption is negligible. And here it's an NdOG solid state laser, diode pumped laser was used for boundary layer heights. I think I don't have to take because people are listening to the LIDAR principle for last 2 days. So this is how the cloud base heights and cloud boundaries and the aerosol layers and boundary layer heights were derived. This is one example to give you how the range corrected the scattering coefficients could be used to understand the cloud base heights and the cloud depth and the boundary layer heights. So this is just one example. So now this is another observation from over Delhi. So this was on campaign mode. So we could get some boundary layer information and under the fog experiment. So coming to the aerosol cloud interactions. So I had a chance to visit under JSPS fellowship to Center for Environmental and Remote Sensing in Chiba University, Japan. So they had a campaign in Cape Hedo, which is Okinawa Island in East China Sea region, wherein in addition to LIDAR, and there was a 94 gigahertz cloud radar, and there were other suite of observations were used. So during my JSPS 10 months visit, I could utilize these data sets to understand how the aerosol affects the cloud droplet size. So how do we estimate the aerosol cloud interactions? So we need to have both cloud and aerosol parameters. So we should, in the aerosol side, we should know what is the extinction coefficient or aerosol loading or CCN concentration. Whereas in cloud side, I think we should have the cloud droplet size or cloud droplet cloud optical thickness. So this is how the I think morning Dr. Prabhakaran mentioned about the fine gold method to estimate the aerosol indirect effect by seeing the relative changes in cloud droplet number concentration or cloud droplet effective radius with the changes in CCN proxies. So here, this is a LIDAR observations were available in that campaign. So this was National Institute of Environmental Studies LIDAR. So these are the attenuated backscatter coefficient for 5 days, and I have selected some cases wherein I have the uniform like clouds were available. So this is from cloud radar and this is from LIDAR. Okay, so for this date, so there is also the 94 gigahertz cloud radar observations. So, uh, so it is. So the mainly the LIDAR network was set up to understand the Asian dust transport there is a lot of dust transfer from China to Japan. So they call it yellow dust events. So to understand this campaign was conducted. So um, there was another case. So which some of the cases I could get wherein all observations were available in LIDAR with aerosols and other in situ measurements and with the radar measurements. So this is the radar data was used to derive the cloud droplet size by assuming there were some assumptions involved because so we were not having directly the cloud droplet number concentration over there. So by assuming the variables, so we could retrieve the cloud droplet size and try to see how the cloud droplet number and the aerosol variables like number concentration with the 0.5 micrometer and scattering coefficient. So what we noticed briefly is that whenever the aerosol scattering was aerosol loading was high, the droplet size got reduced. So this is another case. Like this, some cases were identified and the data were grouped into different liquid water content bins, and the aerosol indirect effect was estimated as given in the earlier equation. The relative changes in droplet effective radius to the changes in aerosol proxy. Aerosol proxy, see, we can see sometimes CCN, sometimes it could be a scattering coefficient, etc. So you have to take a narrow bins of liquid water content, liquid water path. This liquid water path is derived from passive microwave radiometer. So that's what the one technique alone cannot give the complete information. So we have to depend on multiple techniques. So that's why I mentioned, even though I said application of LIDAR in combination with the other techniques. So one technique alone cannot give us all the information. So now coming back to that experience, so then the Ministry of Earth Sciences also were initiated some programs for better understanding on aerosol cloud and precipitation interactions. One of these is KIPEX project, which is cloud aerosol interactions and precipitation enhancement experiment. This was an aircraft-based experiment. The other one is we also established a high-altitude cloud physics laboratory at Mahabaleshwar. It is in the Western Ghats of Maharashtra region. So these are the instrumented aircrafts used in the KIPEX project. So they are the aircrafts were hired from outside. So it was instrumented aircraft. So the experiment was conducted. I'm showing only 2 years, but the experiment was conducted maybe for 3 to 4 years, 4 years. So these are some of the probes used in the aircraft. So they are also using the optical techniques, cloud droplet probe, because so we were measuring both aerosols and the cloud microphysical properties. So these are some of the probes used for cloud measurements, ranging from up to 50 micrometer droplets, and the other one can image the cloud particles up to 1.5 millimeter size. So then there is a hot wire sensor for observing the cloud liquid water content, and there were cloud condensation nuclei counter. So the experiment was conducted in different parts of the country. These are some of the flight paths shown in the phase 1 and phase 2 projects, and the phase 3 and phase 4 were mainly focused in the rain shadow region near in Maharashtra. So this also you can see that how the second indirect effect, like suppression of warm rain initiation, can be clearly seen from these vertical profiles of cloud droplet size distribution. So this was taken somewhere in the Pathankot region in the northern part of India. It is in the May, and what you see at different colors are the last 4 digits give you information about the height at which these observations were taken. So when we say 4546, it is in meters, 4.5 kilometer. Okay, the other one is 4891. Yeah, so the violet color, what you are seeing is in the 7.4 kilometer. Okay, so if you see almost about 3 kilometer depth, the depth of the cloud, you can see even at 3 kilometer depth. So the warm rain initiation has not yet started. The threshold diameter is about 24 micrometer is the threshold diameter for initiation of warm rain process. So we can see much lesser even at a depth of 3 kilometer. So whereas in the marine clouds, so relatively less polluted, having higher liquid water content, you can see clearly. So the lowest height sampled was about 800 meter, close to coast, Bangalore coast. And the highest height is sampled is about 3.3 kilometer. So you can see that already the cloud droplet spectrum has broadened. So it indicates that the warm rain initiation could be very initiated already here. Okay, so here higher the aerosol pollution in a dry environment can invigorate the cloud by suppressing the warm rain process. So here the cloud invigoration was there, so which we could see the ice phase clouds, and we were measuring the finding the images in precipitation imaging probe. We could see the ice particles at these heights. So the warm rain is suppressed. So the cloud could invigorate into larger depths, and it can lead to the cold cloud processes will take place. So at the end of the flight, we could see a thunderstorm over this region. So in continuation to this aircraft campaign mode observations, so the aircraft campaign modes are having some limitations that you have to coordinate with a lot of agencies like air traffic control and also. So we need to hire, we have to bring it from outside. We don't have highly instrumented aircrafts, so we need to bring it from outside, and it involves a lot of procedures. So by considering all the difficulties, so we IITM established a high altitude cloud physics laboratory, wherein in monsoon we have warm clouds float close to surface, wherein this near surface we have a lot of plenty of aerosols, and so it can interact with the aerosols, and how these aerosols can influence the cloud microphysics. That is the idea of this laboratory. So mainly it serves as a aerosol cloud precipitation interactions test bed and orographic precipitation also. So even though the Western Ghats is a heavily rainfall area, heavily raining area during monsoon, the Mahabaleshwar, which annual rainfall is about 6,000 millimeter. So orographic precipitation, even several rivers originate, even Krishna originates from here, going all the way up to Andhra Pradesh and Tamil Nadu. And so these are the experimental facilities available at high altitude cloud physics laboratory for studying the aerosol cloud precipitation interaction processes. So we have for aerosols, we have several suite of instruments. I think then for clouds and precipitation, the radars were also deployed. So these are the facilities. You all are welcome to visit sometime to the this lab to understand the work going on here. So you can see how the aerosols. So what is the variability of aerosol and cloud condensation nuclei? And these are some seasonal diurnal variation. You can see different seasons have different diurnal patterns, and the CCN also has a similar diurnal pattern, right? And what you notice here is the activation fraction is nothing but the ratio between CCN to aerosols. If all aerosols get activated as CCN, then the fraction is 1, right? So what you can clearly see in the early morning hours, you have a higher activation fraction, whereas during daytime, you have more aerosols, but the activation fraction gets reduced mainly because of all these biogenic and anthropogenic sources emits smaller particles and it has a complex chemical composition, so which leads to the reduction in activation fraction. So which currently we are trying to understand how the aerosol chemistry, size, and hygroscopicity can play a role in the CCN activity. And the other thing is that how the cloud droplet, cloud microphysical properties can be measured using cloud probes. So similar to one we use in aircraft, but you can see here also the laser is used. So only the forward scattering the technique is used to get the in situ measurements of cloud droplet size distribution. So you can get the cloud droplet number concentration and the effective radius or mean droplet size. All these information could be derived in combination with the two probes. Even the larger size particles also can see. Cloud droplet probe and the CIP is cloud imaging probe. So by combining, you can get almost 2-3 orders of size ranges. So this gives information about how the cloud aerosol concentration and the cloud droplet number concentration, if you measure simultaneously, you can relate. So how it is changing, how the aerosol concentration is altering the cloud droplet number concentration, and to understand the aerosol cloud interactions. So we can see, so this, you can look at aerosol concentration and cloud condensation nuclei concentration and cloud droplet number concentration. The other panel is effective diameter. So one gives the information, the increase in aerosols, what it does to the number concentration and what it does to the size. Okay, so if there are higher aerosols and higher CCN concentration, then there will be higher droplet number concentration. Higher the droplet number concentration, there's a reduction in droplet size. So that's what we are showing. This way the indirect effect is estimated. So there are some papers which you can go through to understand more about how the indirect effects were estimated. So one thing we noticed is that there is a discrepancy in aerosol cloud interaction estimates when you consider number concentration and cloud droplet size. So there is a systematic bias in that. So we were wondering why there is bias, and we also look at the increase in aerosol not only changes the droplet number concentration, it also changes the dispersion of the cloud droplet size distribution. If you can estimate that dispersion offset, and if you correct it, then there is both the estimates are like similar. So this is in models, if they are using to estimate the indirect effect using the number concentration of clouds, then there could be a higher bias in the indirect effect estimate. And this is a time series of annual variation of integrated vapor and integrated liquid derived from passive microwave radiometer. And you can clearly see in the monsoon season, you have high vapor and liquid, and there is a rainfall also, correspondingly higher rainfall occurs. So coming to the, in addition to LIDAR, if you have radar, so you can get more information on cloud size, because cloud and precipitation side. So even in radar, one radar cannot give full information. So we have to use a combination of centimeter and millimeter wavelength radars to understand the non-precipitating clouds, because so these are the two radars we deployed in Western Ghats. One is cloud radar, K-band, the 35 GHz radar, and the X-band radar. We can see clearly the radar observations for the same type of event, you can see when there is when you observe with the millimeter wavelength radar, you have more finer details in the cloud structures. So this is one such cloud profile, cloud radar reflectivity data. And we can also get all these information with the polarimetric variables, clearly the melting layer and the precipitation fall streaks. So we can also study the mixed phase clouds. In addition, we also try to look at the ice nucleating particles to understand the aerosol cloud interactions. So if you see, if there are more ice nuclei, there could be more ice and precipitation, leads to shorter life of cloud in the lower altitudes. And if there are a few ice nuclei, then cirrus will form at a higher height. So this leads to a net warming effect. So we also implemented the ice nuclei measurements over Western Ghats to understand, as compared to CCN, ice nuclei are very less. Maybe 1 in a million aerosols, there could be ice nuclei can get activated. So we'll try to look at how these aerosol concentration could be used to parameterize the ice nuclei concentration, because we cannot have ice nuclei measurements everywhere. This is a seasonal variability, and we try to see, compared with the existing parameterization schemes, only with the temperature and also with the coarse mode aerosol concentration. This is one such paper last year we had on development of parameterization of ice nuclei in terms of temperature and coarse mode aerosol concentration. So these are the ongoing future works at HSCPL. We are currently working on to understand how the chemical composition using chemical composition and hygroscopicity can modify the CCN activation processes. We also try to, in collaboration with the modeling group, because we are trying to use some models also as a tool to validate the model simulations of the observations. We're also looking at the volatile organic compounds and how this also will play a role in secondary organic aerosols and the cloud condensation nuclei activation. So to summarize, so as we all understood that aerosol particles is a necessary ingredient for cloud droplet formation and ice nucleation processes. And aerosols can modify cloud microphysics to generate feedbacks that may amplify or dampen their influence. Observations are essential for process studies, and LIDAR is one of the major techniques for both aerosol and cloud measurements in terms of altitude distribution of aerosol extinction coefficient, particle shapes, and cloud boundaries and winds. So with this, I will stop my talk and I'll be happy to have some questions. Thank you.
Any participants, any question, please? Online participants and offline participants.
Can I?
Yes, sir. Yes, sir. Please.
Yeah, Pandithurai ji, that very comprehensive and very nice talk about cloud aerosol interaction. I think it will be very useful for the young colleague if you can say like that from the LIDAR and from the cloud radar. Suppose if you measure the cloud properties, like with the Raman LIDAR also we measure the cloud microphysical properties, okay, and the cloud radar also gives. So if you very briefly can tell, then I think it will be very useful for the newcomers. What is the advantages and limitations of LIDAR for cloud study, and what is advantages and limitation of studying the cloud microphysical property using radar? That is just my.
Okay. Thank you for the good question. See, generally the LIDARs, the radiation will get attenuated due to because of cloud, because it cannot penetrate the full depth of the cloud, whereas the microwave radiation, like 35 gigahertz or 94 gigahertz, we can get the complete profiling to retrieve cloud droplet size. Okay, whereas we may not be able to get complete information from a LIDAR alone. So we have to use in combination with a LIDAR and radar so it will complement each other to get a better information.
Okay, thank you. Thank you. Thank you very much.
Yes, I have one small question, sir. Yes, sir. So when you are the LIDARs at high altitude stations, the problem what we face in my experience is the serious condensation problem on the LIDAR window,
right?
The telescope. So how you are managing that problems?
Yeah, right now I think that this in the high altitude cloud physics laboratory we also have similar problem, but I think the ceilometer having all these heater issues and all, so it is relatively I think we are is better. That's why we have not planned sophisticated LIDAR there. So we wanted to have a simple LIDAR. That's why we ceilometer LIDAR we have put, so that I think so that it has all the heating elements and all to take care of this condensation.
Yes. So in ceilometer you are not facing any attenuation sir, during severe winter times in the near field.
Yeah, I think in the rainy season we have problem, and as you said correctly, there is a condensation issue. But if it is heavy rain case, because this site is also one of the heavily raining area, so but we were able to manage. There is attenuation, it needs some corrections. So that's why you can get the cloud boundaries, not detailed information you cannot get. That's why so we need to have some other complementary observations like radar observations will be better.
Okay, okay, thank you, sir. Is there any question by any audience participants? Please, they can raise the hand or they can unmute themselves and ask. Mr. Tejas, you have any question?
Dr. Pandithurai, this is Ravi Kiran.
Yeah, yes.
Actually, I have a question for you.
Yeah.
In your airborne measurements, you are talking about the minimization or reduction of collision process. Looking at the size distribution of the droplets. So when there is a change in the size distribution of the droplets, that not necessarily indicate the reduction in the collision process or a suppression of rainfall. So how do you shed more light on that using that particular measurement?
Okay. So this is a slide you were talking about, right?
Yes.
Yeah. See these profiles or the cloud drop size distribution got at a different penetration of clouds, ranging from this black one is 4.5 kilometer, and the peak one is somewhere 7.4 kilometer. Okay, and see there is already literature shown that the droplet diameter has to be above 24 micrometer for warm rain initiation to get initiated. Warm rain initiation could get activated. Okay, so here if you see, even at the depth of 3 kilometer, so it does not, see the size distribution is very still narrow as compared to the other one when you take it over coastal region. So here you can see even within 2 kilometer, you have broadening of spectrum got broadened. So here the warm rain initiation will be very easy for it because it is crossed 24 micrometer threshold size. So it will be warm rain initiation can get activated. Whereas here it did not get activated. It cannot because it is not even come to this site 24 micrometer. So that's what the invigoration, because our flight also has a limit that you cannot fly more than 8 kilometers. So we cannot go into cold clouds also due to safety reasons. So this is a cloud invigorated, and it took taken over, the ice processes are taken over. That's what I was showing in the same day. So we could also even measure at the 7 kilometer these ice particles. And so even though there was a suppression in warm rain process, but the cold rain process can, because cloud is invigorating, vertically it is developing. So it will get into, there could be a lot of ice nuclei because of dust presence there, and it led to thunderstorm. So we were, by the time we landed, the campaign was over and landed, we were seeing the thunderstorm.
Thank you, Dr. Pandithurai. It was a very nice overview of all the observations from IITM and your observatory. Thank you.
Yeah, there's one more question by Mr. Tejas.
Hello, sir. Am I audible?
Yeah.
Sir, I wanted to know what's the boundary that you considered for estimating ACI values? Was it like 100 meters or 300 meters from the cloud boundary? The aerosol values that were used for estimating the ACI. So those concentrations, were they just in a typical range from the cloud boundary, or was it through the entire column or something?
So here, if it is in situ measurements, what I was showing with the cloud probe, it is in high altitude lab, we keep it at a place. Okay, the cloud air mass is going through the cloud probe. Okay, so we cannot get the vertical information. Whereas in aircraft, we can intersect at different altitudes and we can get the vertical information. That is the advantage with the remote sensing or aircraft measurements when you compare with the in situ measurements. So in a fixed altitude. So even that is sufficient to understand the aerosol cloud interactions, because we are measuring the cloud droplet number concentration. At the same time, you are measuring the aerosol number concentration and trying to see relative changes in aerosol. What is the changes in the number concentration or droplet size, and in turn you are estimating the indirect effect. Whereas when you want to use the profile information also, then you can look at overall how the droplet size changed in the entire column of the cloud. If you want to kind of use cloud radar, you can look at the cloud radar profile in different aerosol conditions and see how the aerosols are altering the cloud profile itself. It's cloud droplet number concentration at different heights.
Thank you, sir. So does it mean that the aerosols were considered just within the region of the cloud and not towards the boundary or out of it? Is that what you meant from those measurements?
Yeah, so there could be some entrainment effects, so which we have to assume that there is no entrainment in that case.
Sir, also, what would be the effect of increasing LWP on these indirect effects? Were the LWP values considered in these studies, were they low or were they significantly high?
No, you have, because see, when you want to see the changes in cloud droplet size, so you want to make sure that it is due to changes in aerosols, not due to change in LWP, right? So droplet size can change with the increase in LWP also. So if you want to make sure whatever relative changes you are seeing in the cloud droplet size, so that's why we are constraining LWP as constant. So you group the data into different liquid water path bins and look at the effect. But still, there could be other errors also, like adiabaticity and all. But that's why we are grouping the data into different liquid water content bins or liquid water path bins. Yes.
Thank you so much, sir. It was a very great presentation. It was elaborate. Thank you so much.
Thank you very much. I thank our organizers.
Any
Also.
questions?